When we begin to look at 3D modelling, first of all we must understand what model means. It's referred to here as any three-dimensional shape, irrespective of its actual size. For example, we can model everything from a shirt button to an entire supertanker. The word model must not be seen as something to suggest a reduction in scale, as in a model car or model plane. Modelling should be seen as a representation of a shape, regardless of its size. I will use the term CAD modelling also, which simply means computer-aided design. 3D modelling uses axes. Typically, our earliest encounters with axes are through graphs and charts, where we have horizontal x-axis and a vertical y-axis. In this view, where the chart is on a wall or screen, we look at the data head-on from the front. This gives us 2 dimensions, so we have a 2D image. When we move to 3D modelling, we need an extra dimension, as seen here. We have a left to right horizontal axis and a vertical axis before, but we need to look at the data in a different way, from an angle. When we do this, we can also see data near to and far away from our viewpoint. This is our additional dimension. The y-axis is no longer vertically up or down, but in and out. However, these are labelled, how they're labelled is a user preference. These axes are coloured red for X, green for Y, and blue for Z. Most common CAD applications represent these colours in a view cube as seen here, or by colouring the major axis lines in the viewports. Some people prefer to swap the Y and Z axes, so for example, Y would be up. However, it's generally good practice to use Z up when applied to 3D printing, as explained in the next image. 3D printers generally refer to the vertical axis as the Z axis. If you make 3D CAD models in software with what is known as Z up, the model you bring in will always be in the correct orientation. If you have Y up in your CAD software, your models will be on the side when you prepare to print them. 3D modelling should not be seen as a huge learning curve, as you already know how to model from childhood toys. You build using basic blocks, adding them together gradually until your desired form has been achieved. These structures have width, depth and height, and so do 3D CAD models. Once you have a basic grasp on some basic tools, you can begin to create 3D models. Just like toy building blocks, every CAD software application comes with some basic shapes to get you started. These are commonly known as primitives and take the form of spheres, cubes, cylinders and cones, but there are others. The main difference, however, is that toy building blocks cannot be modified after you've placed them, they're finite. 3D CAD models, however, can be modified after they've been placed. From left to right, here we can see that the cube primitive is being extended in the vertical or Z-plane to create additional height. Any of the 6 faces of the cube can be extended along an axis perpendicular to its face. Indeed, any flat surface, irrespective of its 2D shape, can be extruded. In the middle, there are 2 examples of Boolean operations. Booleans allow 2 separate objects to have a joint or union which would result in just one remaining object, as seen on the left. Conversely, we can use one object as a cutting tool to remove material from another object. You can see on the right middle image where the sphere has been used to cut the corner out of the cube and the cylinder has been used to cut a circular hole. There's also an option to intersect, which would only leave an object where 2 objects pass through or intersected each other. By using these primitive shapes and a combination of different Boolean operations, objects can be made with generally little effort. By using and modifying primitives, many scene elements can be created when drafting and laying out a 3D model. This photograph on the left has been visualized on the right as a series of primitives to serve as a guide when beginning to model the scene. You can see how some cubes may be elongated to produce oblongs of different sizes. CAD models can also be made using solid body operations from line sketches. First of all, a sketch is drawn on a vertical or ground plane, then tools are used as shown here from left to right. The revolve tool uses half the shape of the bottle as seen in the blue outline, then revolves this around the vertical blue line to create a solid. This is similar to how traditional paper lanterns unfold. The sweep tool needs just 2 sketches. The first one is the cross section, seen here as a hexagon. The long curved line is then drawn before the hexagon is swept along it to make the solid. This is useful for modelling power cords or pipes. The extrude tool essentially takes a 2D drawing and extends it along a path perpendicular or normal to it, shown by the blue arrow. This creates a solid body. A slight taper can be applied to make it wider or narrower at the top, but this isn't shown here. On the right side is the loft tool. This takes a series of 2D sketches separated vertically, then the CAD software computes how to join them together in the most efficient way. Additional guide rails can be used to further refine the shape. Once solid bodies have been made, they can be changed using a series of modification tools shown here. Fillets and chamfers take the hard edges of solid bodies with either a slant or a curve. The shell tool requests an opening surface to be selected before the inside is hollowed out like a Halloween pumpkin to leave an equal thickness inside. The split tool uses a plane or line to indicate a place to cut. The CAD software then slices the solid to create two solids, each of which can be further modified. To gain precision and control over 3D models such as this cylinder, we can use parametric modelling derived from the word parameter. So a parametric model is one which is defined by dimensions and constraints. Constraints are limits on what model elements can and cannot do, such as remaining horizontal or tangent to another object. This cylinder diameter has been assigned a value of 50 mm, then extruded upwards by 40 mm. As the diameter of the cylinder is defined by a parameter, we can change it by altering the value of that parameter, as seen here. The 3D model timeline, seen below, shows two stages, a sketch and an extrude. The change of parameter will only affect the sketch, but as the cylinder was extruded from the sketch, it also updates to the new dimension. The height of the extrude was not given a parameter, but it could be. We can also use simple associative formulas, such as always making the extrude height the same as the diameter, or even half or double it. The previous modelling tools produce solid volumes or models with a degree of thickness. These can be 3D printed as they represent a shape in 3 dimensions. Surface modelling produces only the external aspects of an object. It relies on a number of sketches that a surface is then adapted over. Think of this like draping fabric over a skeletal form. The fabric conforms to the differences between the geometry created by the frame. Surface models like these seen here can be thickened afterwards to create a 3D printable volume. Surface modelling is therefore better suited to more organic shapes and curves like vehicle bodies. This shows the outer surface of a model car, and it has no thickness yet. The surfaces can be easily modified using software. These organic shapes may also be formed using a technique known as Tspline Modelling. The hairdryer model seen here starts as a hollow tube with a number of sections. At the junction of each line or edge we have a point or vertex. When we have more than 2 edges, a face can be made. Each of these, vertex, edges and faces, can be manipulated singly or in groups to make quite complex shapes with relative ease. Thank you.